Good morning, everyone. Today we will see branch and bound approach for solving knapsack problem in algorithm analysis. First, we will see what is branch and bound approach. It is mainly used for solving optimization problem. Uh, it divides the problem into number of subproblems and solve the subproblem. Each and every level, the subproblem solution is considered for choosing the optimal solution. Each and every level, the subproblem with the minimum value or maximum value can consider as a local optimal solution. For a minimization problem, the minimum value is the best value. For maximization problem, the subproblem has maximum value is the best solution. So at each and every level, we are choosing the best uh, subproblem. There is a local optimal that can be explored to the next level. That is called branch and bound technique. The problem is represented in the form of tree. Root node has initial solution. So that can be explored at a first level. So number of possibilities is called branch. Number of possibilities for solving the initial solution. That is the initial subproblem. That is called branching. Number of possibilities is called number of branching. Then at this level, solve all the problems, choose the best one. Other subproblems are pruned, removed from the solution space. So that implementation of branch and bound technique represented in the form of tree structures. It has four important process: exploration, branching, bounding, and pruning. Here, knapsack problem, there is a maximization problem. That is finding most valuable subset that fit into the knapsack. So there are n items given. N items have weight and value. So we have to choose the uh, subset of items from the given set. Uh, that should that we have to put into the knapsack with constraints. That is, total weight of the item in the knapsack should be less than or equal to knapsack capacity, and also the value is maximum. This is called most valuable subset of items that fit into the knapsack is called knapsack problem. So most valuable is maximization problems, optimization, maximization problem. So we are taking the upper bound value for bounding or pruning. So it's a maximization problem. We are taking which problem has maximum value. That is considered as a best solution at a particular level. This is called upper bound function. And what is 01 knapsack problem? Binary selection. 1 means item is selected, included in the knapsack. 0 means item is excluded, not added in the item. And all weight and value should be positive. Each item has weight and value. The weight and value are positive integers. The state space tree node is expanded when total weight is less than W. Node is pruned if total weight is greater than W. So the knapsack capacity is given. We have to add the items one by one till it reach the knapsack capacity. If it exceeds the knapsack capacity, that will be stopped. That can be pruned from the solution space. Upper bound function is used to find the maximum profit. So we are using UB function to find the maximum value for all the subproblems. There are more than one live nodes. The live node having maximum upper bound is considered as a promising node. That is, the node has maximum upper bound value. That is, that will lead to a global optimal solution. That is called a promising node. Other nodes are called not promising. That will not lead to a optimal solution for the next level. So we are pruning non-promising node and we are choosing only the promising node which leads to a optimal global solution. And problem statement is to find the most valuable or most profit subset of items that fit into the knapsack capacity W, capital W. given. N items are given with small w, weight and value. So we are finding value by um, value or profit. That any terms can be used, value or profit. And the knapsack capacity is given, that is capital W. What is the result output of the problem? Select subset of items with maximum profit that fit into the knapsack. So what's the constraint for this problem? So the solution satisfies the constraint is called feasible solution. One problem can have more than one feasible solution because many solution can satisfy the constraints. So that is called feasible solution. Among the feasible solution, we have to choose the best one. That is called optimal solution. So objective function is upper bound function. The value with maximum profit. So the total weight of the selected item should not exceed the knapsack capacity. That is I equal to 1 to 1. There are n items. Xi value is 1 means the item is selected. Xi means Xi is equal to 1 means the item I is selected, added to the knapsack. Xi is 0 means the item is not added to the knapsack. If item is added, 1 into the weight is added. Sum of weight of subset is considered. That should be less than or equal to knapsack capacity. So, if the item is not added, xi is 0. The ith item is not added, xi is 0. So, 0 into weight, ending 0. So, the item is not added into the knapsack. So, x is 0, item is selected, x is 1, not selected, x is 1 means the item is selected. That is called constraint. Total weight of the item with the subset should be less than or equal to knapsack capacity. That is a constraint. So the solution satisfies the constraint is called feasible solution. And what is objective function? So optimal value. How to find the optimal value? Here is a maximization problem. So objective function is upper bound function. So maximize the profit. So sigma I equal to 1 to n xi pi or VI, value or profit. Any term can be taken VI. But if it is I is equal to 1 means, that is xi value is 0 means the item is not added. 0 into value not added. If item I is added to the knapsack, so xi is 1, 1 into value. So the value is added to the upper bound function. So we are adding all the items added in the knapsack value to get the maximum upper bound function value. That should be maximum. Maximize the profit. I equal to 1 to n xi vi. This is called knapsack problem. And we will see one example. Solve the following knapsack problem using branch and bound method. Knapsack capacity is given 10. So there are 4 items with the weight and value. Or value or profit. Any term can be taken. So there are 4 items with weight and profit. Step 1. Find the ratio of V by W. V by W. So the last column V by W ratio. Value 40 divided by 4, 10, 42 divided by 7, 6, 25 divided by 5, 5, 12 divided by 3, 4. So last column V by W is calculated. That is the first step. Second step, sort the items in descending order of V by W. So see the right V by W column that we have to sort in descending order. Descending order means maximum value first. So it's already in descending order. So no need to sort. So 10, 6, 5, 4. That items are already in order. And what is the upper bound function formula? Upper bound UB equal to V. Small v is value plus capital W minus small w. Capital W is knapsack capacity. Small w is weight of the item into VI plus 1 divided by WI plus 1. If you are finding UB value for item, so we have to take ratio of I plus 1 items, VI plus 1, WI plus 1. And see the state space tree. Initially, the item is not added in the knapsack. So V equal to 0, W equal to 0. So substitute V equal to 0, W is equal to 0 in this formula. W is 0. 0 into 0 minus 0 into any value. That is 0 minus 0 is 0 into VA plus 1, 6. What is V value? Substitute the value, find out the upper bound, that is 100. See how we are calculating. V equal to 0, W equal to 0. And then capital W minus small w. Capital W is 10. 10 minus 0 into next item ratio is 10. So 10 into 10, 100. So this is upper bound is 100 for root node. And we have constructed tree. Take the items one by one. So there are 4 items. Take item 1, item 2, item 3, item 4 in different levels. So first we are taking the item 1. So there are 2 edges, left edge, right edge. Left edge is with the adding item. The right edge is without adding item 1. So left edge, if you are adding item 1 in the knapsack, so item 1 weight is 4. So previous the root value weight is 0. We are adding item 1 weight. So 0 plus 4 is 4. Now the weight of the knapsack is 4. Initially value is 0. Item 1 value is 40. So 40 plus 0. Now the node 1 is V equal to 40, W equal to 4. Now find the upper bound value by using the formula. See, for node 1, V equal to 40, W equal to 4. So upper bound is equal to V plus 40 plus knapsack capacity capital W remains same for all the for entire problem. So capital W knapsack 10 minus current item weight is 4 into next item ratio is, you are taking the first item, next item ratio is 6. See, the next second item ratio is 6. So for first item, take the ratio of second item. So that is 6. Substitute the value, we are finding upper bound is equal to 76. And for the node 2, without adding item, so V equal to 0, W equal to 0. Just find the upper bound value. 0 plus 10 minus 0, the 60. So compare node 1 and node 2. See, node 1 upper bound value is 76. And node 2 upper bound value is 60. So this is maximization problem. At this level, we are taking the local optimal. So node 1 UB value is maximum, then node 2 value. So node 2 is removed, non-promising node that will not lead to a solution. So that can be pruned. Node 2 is removed. Now node 1 is a promising node with maximum upper bound value that can be expanded to the next level. That is local optimal. So each and every level we are choosing the node with a maximum UB value. So the at first level UB is 76 that can be selected as a local optimal that can be expanded to the next level. So that's called promising node. Next, take the second item with item 2, without item 2. So with the item 2, what's the weight of item 2? That is 6. So already we have weight with adding item 2. The second item weight is 7. So second item weight is 7. So previously knapsack has 4 kg. If you are adding 7 kg, that weight becomes 11. So we can't add item 2 because it exceeds knapsack capacity, not feasible. 11 is greater than knapsack capacity W. So not feasible. That can be removed. So the right side without item 2. So we are not adding item 2, but the upper bound value will change because of the ratio of next item. Now we are taking second item. To find the upper bound value, we are taking the ratio of third one. So if you substitute the value, we are getting node 4 value is upper bound is 70. Now, what are the live nodes? Node 2 and 4. So we have to consider node 2 also because there are live nodes. Now node 2 and 4. So node 4 has a maximum value. So node 4 can be expanded to the next level. So we are taking third item. Third item weight is 5 kg. See, third item weight is 5 kg. Now we have two edges with adding item 3. Right side is without adding item 3. So with adding item 3, so value will become 65 and weight will be previously 4 kg. Now item 3 weight is 5 kg. So new weight is 9. So find the upper bound value, that is 69. And like that, find out the value of node 6, that is 64. Now there are 3 live nodes, node 2, node 5 and node 6. Among these 3 live nodes, node 5 is optimal because it has maximum UB value 69, which is greater than 60 and 64. Now we are considering node 5 as a promising node that can be expanded to the next level. Now we are taking fourth item. Fourth item weight is 3 kg. See, the last item, fourth item weight is 3 kg. Now weight becomes 12. That exceeds knapsack capacity 10 kg. So that is not feasible. See the right side without adding item 4. So V and W is same, but the upper bound value will change. So how to find the upper bound value for last node? What's the next ratio? So that is 0, because for the last item there is no next item. So how to take Vi plus 1 divided by Wi plus 1? That is 0. So for node 8, V equal to 65, W equal to 9. Find the upper bound value, 65 plus 10 minus 1 into 0, 65. So now node 8 upper bound value is 65. Now what are the live nodes? Node 8, node 6 and node 2. So among these 3, node 8 has maximum upper bound value 65. That is the optimal solution. So once you got optimal solution, see the path from root node to node 0 to that node 8. See the path. So that is with 1, without 2, with 3, without 4. So see the path. Take the item only with adding. So see the first item with 1. Item 1 is added. We can consider the item 1. See the next path. The next edge in the next level without adding item 2. So item 2 should not be added in the solution set. Next with item 3. So 3 can be added. So without adding 4 next. So 4 cannot be added. So in this path, from the solution root node to solution node, the path is taken. In this path, take only the edge with adding. So 1 and 3 is a with 3, with adding item 1, with adding item 3. So that is the value. Finding most valuable subset. Consider the optimal path from root node to optimal solution. Take the item which are added in the optimal path. So item 1 and 3 is added. So item 1 and 3 can be added with maximum value of 65. This is most valuable subset for the given problem. So the basic thing is we have to construct a state space tree. Initially the item is not added. Then find out the upper bound value. Take the items one by one in descending order of Vi divided by Wi, the ratio, and add the items one by one in the level. Each and every level, find out the live nodes. That is leaf node in the tree. All can be, leaf node can be at any level. So see all leaf nodes. Choose the node with the maximum upper bound value. That is promising. That can be expanded to the next level till all items are added to the knapsack. So this is called optimal solution for finding knapsack problem, zero knapsack problem. And what's the time complexity? That is exponential. 2 power, that is b power d. In the worst case, branch and bound algorithm explores all possibilities like brute force. What is B and what is D? B is number of branching factor, number of possibilities at each level. That is called branching factor. And what is D? Depth of a tree, number of edges from root node to the solution node. The tree is called depth. Number of levels in the state space tree is called depth of a tree. So the time complexity is order of B power D. So there is exponential branching factor and depth of a tree. So branch and bound method for solving zero and knapsack problem takes time in exponential order. That is, time complexity is order of B power D. Thank you.